Assalamu alaikum and hello everyone. Good evening for the extra class for the week 2. Today we have a fluid mechanics session on pressure. Okay. So I hope you guys can hear me. If you guys can hear me, then I'm going to start the lecture today. Okay. Today's lecture will be a little bit on theory and we will do some problem solving also. So perhaps at least you guys have some hands-on on problem solving also. Okay. So today's class is all about pressure. Okay. In the last class we studied about fluid mechanics. What is fluid mechanics? What is fluid? What is density? What is specific gravity? What is specific volume? What are the different fluid properties? What are the units? What is viscosity? How the viscosity formula is derived? So today we are going to study a very important property, which is pressure. Fluid mechanics is all about pressure, because the best thing that a fluid can do or a fluid can exert is pressure. Okay. So obviously you guys have gone through the basic definition of pressure already in your undergraduate classes in solid mechanics perhaps, or in other types of science subject, that pressure is basically force per unit area, how much amount of force is exerted on a specific amount of area. Okay. So the formula for pressure is equals to force per unit area. But the thing is that in fluid mechanics, the pressure is fluid pressure per unit area, whereas in solid mechanics, it is normal. The pressure is called normal stress because the force per unit area in solid mechanics is normal stress. How much is the stress acting perpendicular to the surface? However, in fluid mechanics, it's basically the fluid pressure. The whole fluid is basically acting on the surface. So usually people denote it as simple pressure only. There is no need to call fluid pressure. So in fluid mechanics, the pressure is force per unit area, and its unit is Newton per meter square, which is same as solid mechanics. However, in fluid mechanics, the pressure is also converted in terms of another unit which is called bar, BAR. Okay. So in fluid mechanics, 1 bar is equals to 10 to the power 5 Pascal. Newton per meter square is also called Pascal. Newton per meter square is called pascals. So in fluid mechanics, if I say that I've got 1 bar of pressure, it means 10 to the power 5 pascals. Okay, this is equals to 100 kilopascals, or this is equals to 0.1 megapascal. Okay, 1 mega means 10 to the power 6. So this is the unit of pressure. Pressure is also given or denoted in terms of atmospheres. Okay, so we have got something like an atmospheric pressure acting on us. So 1 atmospheric pressure which is acting on us, the atmospheric pressure of the air which is currently on us is equals to 1 atm. 1 atm means 1 atmospheres, and 1 atmosphere is equals to 101,325 pascals. So if I tell you that the air normal temperature and pressure, then you will say that for normal temperature, the pressure of air is 101,325 Pascal, or 101.3, this is common, 0.325 kilopascal. Okay. So these are some of the units of pressure. Okay. So this was quite simple. Okay. So you also know that if you have a large amount of area, okay, then the force or the pressure is reduced per unit area. However, if you got a very small area, then you can easily hammer the nail into the wall, because the area is very small and the amount of force which goes through that small area creates a lot of pressure. So this is just a generalization of pressure in terms of area. Small area obviously produce larger pressure for the same amount of force. Now this is a very important. There are different types of pressure. Okay, this is very important to understand. Types of pressure in fluid mechanics. Let's say you have got your mother earth. This is your earth. Okay, and this is your sky or atmosphere. Okay, so above this sky or above this atmosphere, we have got dark vacuum, that is space. Okay, in vacuum or in space, the pressure is zero. The absolute pressure is P is equals to zero. Okay, so when I say that the absolute pressure P is equals to zero, okay, now I'm going to say this atmosphere. I've got atmosphere also. Okay, outside the space pressure is zero. This is atmosphere. So here I've got atmospheric pressure PATM. Okay, this atmospheric pressure is acting on the Earth, on the whole Earth. Okay, so I've got a glass of water here on the Earth. Okay, that glass of water has got fluid inside. That fluid is exerting some pressure also. Okay, so that pressure is called P gauge. Okay, so I've got a vacuum. Okay, outside this outside the atmosphere. Okay, is vacuum. Okay, that is pressure zero. Then I've got atmospheric pressure where the atmosphere starts. That is called P atmospheric. Okay, and then I've got something on the Earth. Okay, I've got a glass of water on this table. Okay, so that is the gauge pressure. Now let's discuss again in another language. So this is my absolute pressure, which is vacuum pressure, which is zero. Outside the Earth, outside the atmosphere of the Earth, we have got vacuum, and the pressure is zero there. Okay. Then I have got the Earth atmosphere. Okay. So this from here to here, from zero to atmosphere, the pressure is called PATM. So from vacuum to the atmosphere, we have got atmospheric pressure. And if I got something on Earth, okay, okay, then the pressure from atmosphere to the Earth is gauge pressure, EGUAG, gauge pressure. What is the reading of gauge on my for my glass of water? So for my glass of water, I attach a gauge, and what is the reading? That is called gauge pressure. Okay. So absolute pressure definition is the actual pressure at a given position. The gauge pressure is the difference between absolute pressure and local atmospheric pressure, and vacuum pressure is the pressure below atmospheric pressure. So any pressure, so any pressure which is below atmospheric pressure is P vacuum, and any pressure which is above the atmosphere is P gauge. Okay, that is why. So absolute pressure I am measuring from space. So let's say I have this Earth, and I've got a glass of water here, and I ask you what is the pressure at this point. Okay, on this glass of water, absolute pressure is acting. How much absolute pressure is acting? What is P absolute? Okay, now on this glass, the total pressure is due to the atmosphere also. Okay, so the total pressure of the atmosphere is acting on the surface of the fluid. So that is P atmospheric. And my glass of water has got water inside, that is also acting some pressure. So that is called gauge pressure, PG, UAG. So the total pressure at this point, P absolute or P total, is equals to P absolute is equals to the atmospheric pressure, which is acting on the surface of the glass, surface of the water, and then the water itself is exerting pressure on the table or anything. So P atmospheric plus P gauge. This is the formula to calculate absolute pressure. Let's say one of the student in the class today, let's see, Mr. Shimal King, he is standing on earth. Okay, Mr. Shimal King is standing on earth. This is Mr. Shimal King. Okay, Mr. Shimal King has, let's say, 50 kg of weight. Okay, Mr. Shimal King has weight equal to 50 kg. Okay, and he is standing on earth, and his shoe size is only 10. Okay, So his shoe size area is, let's say, 10 by 2 centimeter. Okay. So he is exerting a gauge pressure on earth. So he is exerting a pressure because of his weight. Okay. So how much pressure he is exerting? Pressure equals to force over area. Force is mg over area. So his pressure is equals to 50 kg over area is, let's say, 10 into 2 into 9.81. Okay. So let's say his pressure comes out to be 20 kilopascal. Now on top of Mr. Shimal, we have atmosphere. The atmospheric air pressure is also acting on him. Okay. So Mr. Shimal is under the sky. The sky is also putting some pressure, and that pressure is atmospheric pressure. Okay. Just now I told you guys the atmospheric is equals to 101,325 Pascal. Right. So what is the total pressure that is acting on this surface? The total pressure is called the absolute pressure, is P absolute is equals to the atmospheric pressure which is acting on Mr. Shimal. So P atmosphere on Mr. Shimal plus Mr. Shimal's own pressure due to his own weight. So pressure due to weight, which is also called gauge, and this is called atmospheric. So P absolute for Mr. Shimal is equals to 101,325 Pascal plus 20 kilopascal means 20,000 pascals. So this is the absolute pressure acting on that surface on which Mr. Shimal is standing. So understood, guys, this concept? Is it okay?
Yes, sir.
Okay. So now let's talk about vacuum. So as I said, above the atmosphere, we have moved towards space. So as we move towards space, the vacuum or negative pressure or vacuum increases. Okay. So that is why when we talk about vacuum, okay, so we have got here pressure is equals to 0. Here we've got atmospheric pressure. Okay. So now you are in this area, not in this area. Here it's gauge pressure, P gauge. Here is vacuum pressure, P vacuum. Okay. So the absolute pressure at this point, if I send Mr. Shimal to outside of the atmosphere, then the absolute pressure, P absolute, is equals to atmospheric pressure minus vacuum pressure. So P vacuum becomes P atmospheric minus P absolute. So this is the answer. So pressure at this point, this is P absolute. P absolute is equals to P atmospheric minus this thing. Okay. So P absolute is equals to, this is P atmospheric minus P vacuum is equals to P absolute. Vacuum, this is atmospheric. So this is the concept of absolute pressure, gauge pressure, and vacuum pressure. Now in fluid mechanics, throughout the course, the pressure is given is absolute pressure unless and until specified. So in the problem, if it is written that the pressure at this point is 20 megapascal, then it means that they are getting the absolute pressure. It means that they are considering the effect of atmosphere also. Okay. Unless and until they say no, the gauge pressure at this point is 20 megapascal, then it means obviously the gauge pressure is 20 megapascal. So this is the thing. Now, how do you find the pressure in a fluid? Okay, pressure increases with ocean depth. Why the pressure increases with respect to the depth? Okay, this is due to an increase in hydrostatic pressure, force per unit area exerted by the liquid on an object. So the weight of a fluid is basically creating pressure, and the higher we go down, the higher the weight of the fluid becomes. So on the top surface, you see the amount of weight is less. Then we move down, the amount of volume and weight both increases, and that is why the pressure increases as we go down. If you dive in a swimming pool, on the upper area, the pressure is less. the water pressure that you feel on yourself is very less. As you go down, the amount of water increases, so the pressure on the you also increases. So pressure is basically a function of depth. Okay, pressure increases with respect to height, both for liquids and solid. But for liquids, the amount of pressure that increases is very high. But for gases, not solid, sorry, gases, pressure increases for both gases and liquids. So for gases, the amount of variation of pressure with respect to height is very small. In this room, the pressure is almost equal, almost. But if I fill this room with water, then what is going to happen is the pressure is going to vary a lot. Okay. So let's take an example of Mount Everest. Okay. As you can see, we have got one room. In that room, we have got one atmospheric pressure. Okay. Now this room is 5 meter high. Okay. So if we go down, okay, then the amount of pressure increase is very less, 0.1.006, negligible. However, if you talk about a very long distance, let's say Mount Everest. Mount Everest is 8,850 meters high. Okay, then the amount of pressure difference is very too high. Okay, so on the surface, the pressure is 100 kilopascal. But if we go to the peak of the Mount Everest, the pressure is 30 kilopascal only. So that's quite less, and that is why at Mount Everest the amount of air is less, the pressure is less, so the amount of oxygen available is also very less. So let's talk about pressure on a single point. And what is pressure? Pressure is vector or scalar. Pressure at a point. Pressure is basically a scalar quantity because it does not have a specific direction. When we talk about the body, on this body, the pressure is acting in all the directions. Okay. So there is no specific resultant force which is available. That is why pressure is scalar quantity. It means that it has got only magnitude. Pressure has got only magnitude, but no direction. This direction is not available for pressure. Okay, pressure is not a vector. It is only scalar quantity. Now, how does the pressure varies with respect to height? That is very important to understand. Okay, how does the pressure vary with respect to height? Variation of pressure with respect to height. You already have experienced this in swimming pool, but what is the relationship? How does the pressure vary? What is the relation of pressure increase or decrease? With which variable it increase or decrease? Does it increase or decrease with respect to fluid properties? Does it increase or decrease with respect to the dimensions? What is the relation? We have to make that. Okay. So let's say that we have got a very large swimming pool. Okay. And Mr. Alif, okay, he is swimming, enjoying his swimming in deep pool. Okay. So he is a deep diver. Okay. Now here at this point the height is 0. We say z is equal to 0 at this point. Okay. He is swimming here, enjoying his time, diving, watching nature and everything. Okay. So he go to a very large height, let's say at a certain height h. Okay. Now I want to know that how much pressure is acting on him. Okay. He is completely in a sea or in a fluid. He is diving in a fluid. The fluid can be anything: water, sea water, lake water. All have different properties because they have different amount of salt inside. Okay. Now because he is swimming in let's say sea or some lake, so we have got atmospheric pressure which is acting on the surface of the lake or pool. Okay. Atmospheric pressure is denoted by this inverted delta. Okay. This is the indication that atmospheric pressure is acting. Okay. So how much is the pressure which is acting on him? Okay. So the common formula for pressure is force per unit area. Force per unit area. Okay. How much force he is acting based on his weight. Okay. So the force for in this case is equals to his weight. Okay. So pressure equals to W over A. What is W? The formula for W is mg, mass into gravity whole divided by area. Okay. What is mass? Mass is density is equals to mass per unit volume. So mass is equals to density multiplied by volume. Okay. Now let's put this mass value in this equation. So this becomes density into volume into gravity whole divided by area. Now formula for volume is equals to area multiplied by length. Okay. So pressure is equals to area density multiplied by area multiplied by length multiplied by gravity whole divided by area. Area cancel out. So pressure is equals to density into gravity into length, and in our case length is equals to the height of him. Okay. Yeah, this is one thing. We are going to take this height. Okay. Now on this swimmer, Mr. Aleph, how much pressure is acting? The pressure is acting of this whole fluid on him. This whole fluid is acting on him. Pressure. Okay? That is why we take this length on him, and this is the cross-sectional area. Okay. So that is why we say pressure equals to rho g h. The whole fluid pressure is acting on that person. Okay. Now we know that specific gravity s sorry specific volume gamma is equals to rho g. So pressure is equals to gamma into h also. Okay. Let's say I want to integrate this equation. Let's say the integral dp is equals to gamma integral dh. Okay. We have got this point. This point is a point, and this point is atmospheric pressure. At atmospheric pressure, the height is 0, and at point A, the height is h. So the point A, PA, P atmospheric, is equals to h and 0. So PA minus P atmospheric is equals to rho, sorry, gamma into h. Okay. So the total pressure which is acting, absolute pressure which is acting on what you call Mr. Aleph is atmospheric pressure plus his own pressure plus the fluid pressure also, gamma into h. So on Mr. Aleph, okay, we have two pressure. One is the atmospheric pressure plus the pressure which is due to this fluid. Those all atmospheric plus pressure of the fluid is acting on this person. Okay. So this is how pressure varies with respect to what you call with respect to height, and this is how it is done here also. Okay, in this slide. Here they've done through a different way, and I have done through a different way. Now, how much does pressure changes? That's very important. Pressure changes linearly with respect to depth. Okay, so I have got a graph. This is pressure, this is height. So as the height increases, the pressure increases, and it goes linearly. This is straight line linear. Okay. Now, how much is the slope of this line? Like this, it increasing. Like this, it increasing. It depends because pressure now is a function of density, okay, and height. So the fluid is very high density, then obviously the pressure increase will be very high like this. If the fluid pressure is very low, the fluid density is very low, then the height pressure will decrease less with respect to height. Okay? So if I've got a wall, this is my wall, and I fill this wall with liquid. Okay. Then as I move downwards, the pressure increases. As I move downwards, the pressure increases. This is atmospheric pressure. So this is how this also shows. Okay, this figure that we've got three holes at three different locations based on the height, and as the fluid decreases, okay, the pressure here is less. The pressure increases with respect to height, so the water can go further, and then at the bottommost hole, the water goes the furthest. Okay. So that is when we are going to design dams, you can see and observe that the wall thickness is very higher at the lower part rather than at the upper part. Why? Because the pressure increases at the lower part more than the upper part. So this is what I talked about, that for gases, the pressure increases not too much. However, if you talk about mountains, then the pressure increase or decreases very, very high. So the pressure in a liquid at rest increases linearly with the distance from the free surface. Okay, so I showed already the linear relation as well. So whenever you are sucking fluid from with the help of straw, what you do is you suck something, you reduce the pressure in this area. When you reduce the pressure in this area, then the atmospheric pressure pushes that thing in towards your mouth. So when a person sucks through the straw, the pressure in the straw becomes low. The atmospheric pressure outside, which is higher, will force the water into the straw. Okay, so this is the principle. Now, what about pressure value? Okay, so what is the value of pressure in this height and at this height? So this, let's say this is 10 meter, and this is, let's say, 20 meter. Okay. When we talk about pressure, pressure varies only with respect to height, but does not vary with respect to the horizontal distance. So the pressure here, 10 meter is going to be same. P1 point is equals to P2 point is equals to P3 point. Similarly, the pressure on the 20 meter, these pressures on the surface is same. P4 equals to P5 equals to P6. So pressure varies only with respect to height, but does not vary with respect to uh, the horizontal surface. So if you can see in this figure, we have got water and then we have got a height h. So the point A, B, C, D, E, F, G are at same height, so the pressure is same. However, if you see this I point and H point, they are also at the same height, but the pressure is not same. Why? Because the one of the conditions is that the fluids should be same. However, here the fluid is mercury. Mercury has is around 13.6 times heavier than, it has a more specific gravity. So the mercury is exerting more pressure. So if there is water here, then obviously H and I have same pressure. But once we put mercury, then the mercury is exerting higher pressure. So the pressure at point H is not equal to pressure at point I. Okay, that is very important. Let's say I have got a U tube. This is a U tube. Okay. In the U tube, this has water inside. Okay. So the pressure in this horizontal line at this point, let's say this is point 1, and at this point, let's say this is point 2. So pressure at point 1 is equals to pressure at point 2 because they are at the same level. However, if I say that I've got a U-tube manometer, okay, we have got fluid here, and then we've got a different fluid here. Okay, now this and this height is different. So the pressure at this point P2 and the pressure at this point P1 is not equal because there is a height difference. Okay, so that is important to consider. When is pressure equal and when is pressure not equal? So the pressure is same on all points on horizontal plane in a given fluid regardless of geometry, provided that the points are interconnected by the same fluid. This is the important condition, same fluid condition. Okay, so let's move on to the first pressure measuring device, which is called a barometer. So let us move to pressure measuring devices. There are many types. Number one is barometer. Number two is manometer, and so on. The function of barometer is to measure atmospheric pressure. Function is to measure atmospheric pressure. The function of manometer is to measure pressure difference or measure pressure at a point, at a certain point, or it can measure pressure difference delta P. It can measure pressure difference delta P. Okay. So how does barometer measures atmospheric pressure? We have got uh, we have got a tank, okay, a very small tank. Inside I've got mercury, Hg. Mercury is denoted by Hg. Mercury is the only liquid form of metal. So I've got mercury Hg inside, and there is got a very small tube, inverted tube inside. Okay. What happens is that when the atmospheric pressure exert on this mercury surface, okay, what happens is that the mercury rises at a certain height. That is called mercury column height. This rise in height is called in mercury column height. Okay. So for one atmosphere, okay, the height that the mercury will increase, height of mercury increase is equals to 760 millimeter. So if you take this device to mountain, the atmospheric pressure will decrease. So when the atmospheric pressure will decrease, the height of this column will also decrease because less amount of pressure is acting on the surface, so it is not pushing the mercury out up into the tube. Okay. So this device is used to measure atmospheric pressure PATM. This is equals to the density of mercury multiplied by gravity multiplied by the height of the column. It is to be noted that the length of the tube, okay, if the tube is very thick, doesn't matter. Thick tube, thin tube, long tube, doesn't matter. Okay, for the case of barometer. So this was the concept of barometer. So why we use mercury and why we don't use water? Because the if water is taken instead of mercury, then you see what happens. Under 1 atmosphere, the height of mercury column increases 76 centimeter, okay, or 760 millimeter. Density of mercury is 13.6 into 10 to the power 3 kilogram per meter cube. Now the density of water is only 1000. Okay, it is very less. It is 13.6 times lesser. Okay, so the height of the water column will be 13.6 times higher. So 760 multiplied by 13.6. So it will be a very large tube if you want to measure atmospheric pressure. Okay? So that is why we use the densest fluid on Earth, which is, I think, mercury, one of the densest, and then use it for measuring temperature for your kids. Okay, or sorry, not temperature, pressure for your atmosphere. But mercury is used also for the same purpose of measuring temperature also for kids and for fever patients, etc. So let us do one exercise. Okay. So we have got example 3.2. Let's do the first exercise of fluid mechanics. Okay. Now, as I said to you guys, there is a way of solving something, right? So let's write the given data first. The first thing you need to do is write given data. Determine the atmospheric pressure at a location. So we have to find out atmospheric pressure PATN. Pressure atmospheric is PATN. We have to find at a location where the barometer is reading 740 millimeter Hg. So height of the barometer is 740 millimeter Hg. So 760 is equal to atmospheric pressure. So the height is reduced. The height is reduced means the atmospheric pressure has reduced also. Now gravity at that location, gravity is also reduced. Okay, 9.805 meter per second square. Assume the temperature. So assumptions has to be written. Assumptions that we have temperature is equals to 10 degrees centigrade, and at that temperature the density of mercury, density is rho of Hg is equals to 13570 kilogram per meter cube. So this is given data. Out of 10 marks, I will give you 3 marks for given data. Now you should write the formula, applied formula. So applied formula. Okay, we go back and see what was the formula. So atmospheric pressure PATM is equal to density of mercury or Hg multiplied by gravity multiplied by height of the column. Okay, so solution or calculation. So you write applied formula, you can get 2 marks. Atmospheric pressure PATM is equals to density is 13570 multiplied by 9.805 multiplied by the height is 740 millimeter, right? So this it is in millimeter. This is the unit is in millimeter. Need to convert it into meter. So 740 millimeter divided by 1000 is equals to 0.740 meter. So I put the 0.704740 0.740. So atmospheric pressure comes out to be 98.5 kilopascal at that location. The normal atmospheric pressure is 101 kilopascal. So obviously we are climbing mountain and the pressure has reduced. So the person is climbing mountain going up. Okay, that is why the pressure is reducing. So is it clear, guys? If clear, then I will proceed.
Clear, sir.
So let us move to another problem, exercise 3.3. Problem number 3.3. So intravenous injection. So you have got injection they're putting on your head, on your hand. Okay. Most of you guys have gone through maybe accident or something already. So I hope not, but many people have good experience. So they already experienced this injection. Okay, intravenous, and then you got a drip at a certain height. Okay. So how much the height will create a pressure on your hand? If the height of the drip is small, the pressure inside goes is also very small and the flow rate is less. And if you put the height very high, then the amount of pressure on your hand also increases. So let's see how what happens in this numerical. So this guy has got an accident and he is lying down. Okay, on his hand we have got this intravenous drip, and the tube is going into his hand. Okay, this bottle is called IV intravenous bottle, IV intravenous, and this infusion is called intravenous infusion. So intravenous infusion usually are driven by gravity. So the fluid is driven into this man by the help of gravity by hanging the fluid bottle at a sufficient height. Now the height should be sufficient. If the height is not sufficient, maybe the blood will also go into the drip. So very important to control the height. So it is very sufficient height to counteract the blood pressure, because the blood also is creating. This is a pump inside, right? I have got my heart. My heart is pumping, causing pressure inside the vein. So the blood will come out of the vein because of the pressure. So when I'm going to connect the needle here, okay, the blood wants to come out also. So we have to counter the blood coming out by putting additional pressure. So when we put additional pressure, then the blood goes back inside. Okay, so when you are going to cut yourself, the blood comes out because the heart pumping. When the heart pumping, then the blood comes out. So to push back the blood during this, we have to increase the pressure so the blood does not come out and the fluid goes inside. So this is the trick. So so we need sufficient height of the drip. Okay, and this is shown in the figure. So the higher the bottle is raised, the higher the flow rate it is. Okay, so the higher the amount of liquid that goes inside. It is observed that the fluid and the blood pressure balance each other when the bottle is 1.2 meter above the arm level. So this is the arm level. The bottle is 1.2 meter above the arm level. Determine the gauge pressure of the blood. Okay, so let's write given data. Okay, so given data. Uh, so the bottle is 1.2 meter above. So the height is equals to 1.2 meters. Okay, and the pressure required is determine gauge pressure P gauge of blood. Okay. Now they have not given the density, or they have given the density. Take the density of fluid to be 1020. So the density rho of blood of the fluid, sorry, because this fluid is exerting the pressure. The fluid in the drip is exerting the pressure. So density of fluid is 1020 kilogram per meter cube. Okay. Now they are saying determine the gauge pressure of the blood when the pressure in the blood. So at this point, when we put the injection, the pressure of the blood and the pressure of the drip both are equal. So the blood not coming out, the fluid, intravenous fluid not going in. So it balance, exact balance. So at this point, what is the gauge pressure? Okay, when the blood cannot come out, and when the blood pressure and the intravenous pressure is equal. So P pressure blood is equals to pressure intravenous fluid. So I will write condition number 1, pressure of intravenous fluid IV is equals to pressure of blood. Okay. So he's asking. So let's calculate what is the pressure in IV is equals to rho density of IV multiplied by gravity multiplied by height. So pressure IV. This is the formula, applied formula. Then we go to solution. So density is 1020 kilogram per meter cube multiplied by 9.81 meter per second square multiplied by height is 1.2 meter. So the pressure in IV, which is equals to the pressure of blood, is equals to 1 to 12.007 kilopascal. So this is the gauge pressure. If they ask me what is the absolute pressure here, then what I will do, P absolute is equals to P atmospheric plus P gauge. So this is 101 plus 12 is equals to 113 kilopascal. If they ask about absolute, but they did not ask. So this is part number A, solution. Let's move to part B. If the gauge pressure of the fluid at the arm level, so at the arm level, the gauge pressure needs to be 20 kilopascal. So they are given P gauge is equal to 20 kilopascal. Okay. For a sufficient flow rate, determine how high the bottle must be placed. So they're asking about the height. Density is same. Okay. So pressure IV is equals to rho into G into H. Height is equals to pressure whole divided by rho into G. This is equals to 20 kilopascal into 10 to the power 3. Kilopascal into pascal is equals to 10 to the power 3. Multiplied by density is 1020 multiplied by 9.81. So the height of the IV fluid comes out to be 2 meters. So this is the answer. So they told us the pressure here. Now they want to know that how much height is required to make this pressure. How much height is required to make this 20 kilopascal. So we need to be 1.2 meter high so that the pressure here is 20 kilopascal. So is it clear, guys? Understanding, or there is some confusion in this numerical? I can repeat.
Clear, sir.
Okay. Okay. So as you can see that at higher altitude, the pressure is less. When the pressure is less, the amount of oxygen available is less. So the breathing is very difficult and we cannot produce much energy because oxygen required by the muscle is not sufficient. So we cannot do very good work at higher altitude. Similarly, the car engine requires a lot of air. Some people have hoods and those hoods have got some air intakes, big air intakes. So if the air amount of air is very less, then the combustion is very less. When the combustion is very less, then the piston cannot produce a lot of power. When a lot of power is not produced, then car will slow down perhaps, or it will be difficult to operate. So let's move to Pascal law. Pascal's law is basically stating that if I have got this confined cylinder, confined means all the entry and exit are closed. This is an open water bottle. Okay, if I am going to close the lid, okay, if I am going to close the lid, then it becomes confined. Okay, so this term is very important. So a pressure, a consequence of pressure, okay, the cause of pressure, what pressure causes is that a consequence of pressure in fluid remaining constant in horizontal direction is that the pressure applied to confined fluid increases the pressure throughout the same amount. So let's say I've got this, okay, this is for, I've got one piston here, I've got one piston here. Inside fluid confined, confined bottle, confined fluid inside. Okay. Then when I'm going to push this piston down, okay, I push this piston down, this piston will go up. Okay, this is what the law states. So the fluid moves and it moves the upper fluid also. And that happens by the pressure equals to the same amount. Inside, when I'm going to press this fluid, the pressure transmitted is also same. When I'm applying this force on this certain amount of cross-sectional area, a force is applied, it transmits into the fluid. So the pressure is transmitted into the fluid. Okay, that pressure is transmitted into the fluid. Okay, and then it causes the same amount of pressure to go up. So the pressure in this point is equals to the pressure at this point. So when the pressure at point 1 is equals to the pressure at point 2 in a confined space with confined fluid, then force 1 over A1 is equals to force 2 over A2. Okay. So by playing with these areas, by increasing and decreasing this area, I can, by small area, I can create a large force. Okay. By large area, I can create also more displacement, perhaps. Okay, so this is what this hydraulic pulley helps out in lifting the cars. So the hydraulic system, like hydraulic suspension, the hydraulic pulleys, the hydraulic lifters, they are based on this mechanical advantage that the pressure is, there is fluid inside the shocks and that fluid is closed completely. Okay, and then it produces huge amount of pressure. The pressure is fully transmitted. Okay, so this is the principle of Pascal's law. Okay guys, so we will resume the lecture. So let's do one problem, okay, a very simple one. If you guys think, when you guys think it's too much, okay, then let me know, okay, I will stop. So if you think there is too much, then let me know later on. The pencil thinks it's too much. Okay, so let's do this problem, very easy one. Okay, calculate the pressure at point M in a tank shown below. Okay, so we have to calculate the pressure at point M. Before we start this numerical, I've got this empty tank. This tank is empty. I put a gauge here, and that gauge has a meter here. Okay, now if I ask you guys what is the pressure of this empty tank, what is the gauge pressure, what is the gauge pressure of this empty tank, remember that all the gauges in the engineering world, all the gauges are calibrated so that they don't show atmospheric pressure. You see this gauge, you see all of these gauges, okay? These gauges are in an atmosphere, right? All of these gauges are in an atmospheric pressure. They are in normal environment, but the reading is zero, right? The reading is zero. So it means that all the gauges are designed to, and these gauges show gauge pressure. So these gauges show gauge pressure, and we know that gauge pressure does not have atmospheric component. So if I tell you that this tank is empty and I attach a gauge here, then what is the gauge pressure here? So you will say the gauge pressure is zero. Okay? I ask you what is the absolute pressure here? P absolute at this location, at this point, what is the P absolute? So P absolute is equals to P atmospheric plus P gauge. So this P absolute is equals to 101 kilopascal. So the absolute pressure is there. Now let's fill some water inside. Okay. Now let's fill some mercury inside. Okay. Let's fill mercury inside. Okay. I put mercury inside. This mercury has a height of 10 centimeter. This is equals to 0.1 meter. Okay. And now I put inside water also. Dirty water, black. So the height is 0.5 meter. This is water. Okay, and I show here this inverted triangle. You know, this means atmospheric pressure is acting also. So calculate the pressure at point M. At this point M, what is the pressure? Okay. So this point, at this point M, the pressure is the pressure due to mercury, the pressure due to mercury height, okay, the pressure due to water, absolute pressure. Okay. Calculate the absolute pressure at point M. So the atmospheric pressure is acting, then we have got water, then we have got mercury. So pressure mercury plus pressure water plus pressure atmosphere. So what is pressure formula? Pressure formula is rho GH. Now density of mercury, height of mercury, then plus density of pressure of water. What is pressure of water? Rho GS. So density of water, gravity into height of water plus P atmosphere. So the absolute pressure at point M is equals to density of mercury is 13600. Gravity is 9.81. Height is 0.1 plus density of water is 1000. Gravity 9.81. Height is 0.5 plus 101325. Okay. So later on you guys can calculate and let me know the answer. So this is the concept. As we move down, it depends what kind of fluid we have, and then we multiply the density of that fluid with the height. Then the second fluid, the density and height and gravity. So all of them add together as we move down. Okay. So I hope you guys can understand this problem.
Sir,
Yeah.
um, why water does the height of water is not 60 cm?
Because you see, sorry, maybe you guys cannot see, the water height is from here to here only. So it's
It's
50
not include from bottom.
because water here bottom got mercury, another fluid. Water is from top until 50 meters. Below, no water, no water. Below is mercury then. They don't mix. They do not mix.
Okay, okay.
Yeah.
Thank you, sir.
If I say that this tank is full of water and its height is 60 centimeter, then the pressure is only the pressure of water plus P atmospheric. At this point, pressure at point N is water plus atmosphere, because the total height of water is 60 centimeter. But because the water height has been reduced to 50 and I put mercury here, so now the water height reduced to 50 and this one 10. So now I have to add mercury also, like this. So the height of fluid is very, very important, exact height of the fluid. Let's say I've got a very small tube also, okay, and got water here. From here to here I fill water, and from here to here I fill mercury, okay, and the tube is open to atmosphere, okay. So again it will be the same pressure. It doesn't matter small tube, large tube, doesn't matter. The x distance is not in the formula, okay, only the height matters. This height, very, very important to correct the to measure the correct height of water. This is height of mercury, this is density of mercury, this is density of water. So these four parameters are important. So this was one problem. So the manometer barometer problem is finished, and the pressure variation with respect to height problem is also finished. Now we move on to manometer. This is second device. First device was barometer. Now we move on to second device, which is called manometer. Okay. So the function of barometer was to measure the atmospheric pressure in terms of mercury height. Now the function of manometer is to measure pressure, or pressure at that certain point, or measure pressure difference between certain point. Okay. So the function of this is two function, either measure pressure at a point or moderate pressure difference. How does this happen? Let's say I've got two rooms. One is Aleph room and one is the king room. Okay. So I've got two rooms. Okay. I've got room number one and room number two. I connect these rooms with YouTube. Okay. Not the movies YouTube, but the YouTube manometer. Okay. I have connected that. And in this tube, I put mercury. So I put mercury here. Okay. Now the pressure in this room, both room is same. Okay. Both Shamil and King has opened the windows. They open the windows atmospheric inside, and he also opened the window and atmospheric inside. So pressure in room A is equals to pressure in room B. Okay. Now because I put some mercury inside, okay, now the height of the mercury on both sides will be equal, because both rooms are exerting same atmospheric pressure. When though both rooms are exerting same atmospheric pressure, the fluid balance out and become equal. Because Shamil room and King room, window is open. The window is open, same atmospheric pressure inside, and the fluid inside cannot move up, cannot move down, because it is same pressure is acting on both surface of the fluid. So the height is same. So the height is same. Now let's assume that Mr. Shamir closes the windows. Okay. He closed the windows Okay, and he starts a blower compressor inside. So we put a compressor based blower. He wants to, he likes pressures, he likes pressure here inside the room, cool and like very nice. So he put a compressor here. When the compressor is put in his room, the pressure in that room increases. When the pressure in that room increases, it is going to push the fluid downwards. When it is going to push the fluid downwards, the fluid on the left hand side in the Mr. Alif room will increase. So the fluid height will increase here. So you push the fluid down, the fluid goes up. Okay. So how does the manometer looks like? If I draw the manometer again, now the manometer is exerting more pressure because Mr. Shamir increased the compressor. So the fluid moved down, and on the Mr. Alif side, the fluid move up. So this fluid has moved up. How much it move up? You can see the difference. The fluid move up from here to here, this distance h. Okay, so the fluid has moved up this distance h. So manometer is a device which can measure a difference in fluid pressures. So it can measure P A minus P B. Okay, is equals to that. I will let you later how it is calculated. Okay, but you should know how the fluid moves in a manometer and how to know where the pressure is high, where the pressure is low, and you can get the pressure difference by this device. Okay, so manometer is commonly used to measure small to moderate pressure differences. So let's say you've got three types of fluid inside here, okay, H1, H2, H3. Okay, and then we got atmospheric pressure also. So like the previous problem, atmospheric pressure plus fluid pressure 1 plus fluid pressure 2 plus fluid pressure 3 is equals to pressure at point 1. Pressure at point 1 is equals to the fluid and its height plus fluid 2 and its height plus fluid 3 and its height plus atmospheric pressure. Remember that. So we have already done this exercise. Okay, it doesn't matter, remember, how the tube is thick or the tube is thin, doesn't matter. Okay, the pressure remains same and it varies only with respect to height. So this is an example. Okay, determine the pressure of the gasoline water interface at the bottom of the tank given gasoline Sg is to 0.7. If you want to know the at this point, then the pressure is only rho g density of gasoline multiplied by gravity multiplied by height of gasoline. If I want to find the pressure at the bottom, then it is atmospheric pressure plus gasoline pressure plus water temperature. If I want to find the pressure at the interface, then it is atmospheric pressure plus gasoline only, because I want to find the pressure only at the interface. Why they give specific gravity 0.7? Specific gravity Sg is equals to density of substance divided by density of water. So I can calculate the density of gasoline. How? Density of gasoline divided by density of water is equals to 0.7. Density of water is equals to 1000 kilogram per meter cube. So density of gasoline equals to 0.7 multiplied by 1000 is to 7000 kilogram per, sorry, 700 per meter cube. That is why they give the specific gravity of gasoline. So I hope you guys can solve this problem very easy. If there is any problem, let me know. Okay, then I will solve in the class also. Very easy. So a basic manometer can measure pressure difference. A basic manometer can measure the pressure at a certain point also. So let us see how basic manometer works. I have got a gas tank And now with the gas tank, I attach a manometer. The most simple type of manometer. Okay. Now because I attach this manometer with the tank and the tank has gas inside, so that gas is pushing the fluid in the manometer downwards, and if you push downwards this way, it will go up that way. Okay. So the gas is until here. This is gas. This gas is pushing the manometer until here, and then it moves upward in the other direction. If I have two open tanks, if I have a simple manometer right now in my hand, let's say in my hand I have a manometer like this one, then how the fluid look like? Fluid is balanced here. In this manometer, the fluid is balanced because atmospheric pressure is acting on one end and atmospheric pressure is acting on the other end. So that it's balanced already. I am not pressurizing any part. So the fluid is balanced. But now if I attach this to your gas cylinder in your home, you have got gas cylinder, right? Petronas or LPG cylinder. I attach this device to the gas cylinder, okay? Then the manometer will, the fluid in the manometer will be pushed downward and it will go upward the other end, right? So this is what happens when you attach a manometer with the pressurized container. If you don't attach it with a pressurized container, then both ends are same pressure 1 is equals to pressure 2. So if you don't attach it to any container, okay, then the fluid is same height. When the fluid is same height, what does it mean? That pressure at this point is equals to pressure at this point. So P1 is equals to P2. But if I attach it to a gas cylinder, okay, the pressure go down here and the pressure go up here. So at this point, this is P1 and this is P2. So P1 is not equals to P2 because of the height difference between the fluid. Pressure varies with respect to height. Here the height difference is 0. This height difference is H is equals to 0. Height difference is 0, so pressure is same. Height, there is got a height difference and then there is some pressure difference. So there is delta P which exists and we don't know that value. So this is the concept. So now in this picture, we attach a manometer to the gas cylinder. The gas cylinder pressure, put the pressure on one end and on the other end the fluid moves. The manometer fluid moves. We put a fluid, heavy fluid inside a manometer. So this is what happens. Okay. So how to do calculation? How to find the pressure in uh, inside the gas cylinder? Okay. What is the pressure in gas cylinder? This is the question. That's a big question. Now I know that this point and this point is equal. So pressure at this point and pressure at this point, because they are same level, remember the Pascal law. Okay? Pressure at same point, PA is equals to PB, right? So pressure at the left hand side, LHS, is equals to the pressure at the right hand side at this location, which I marked in the figure. Okay, so the pressure, all the pressure which is acting on the left hand side is equals to all the pressure which is acting on the right hand side. Okay, so the question is, what is the pressure on this left hand side? On this left hand side, this is the gas pressure. Okay, let's say this is 0.1. This is gas point gas pressure, P gas. So at this point, all the pressure is gas pressure. Okay, so left hand side, pressure at left hand side is equals to pressure at right hand side. So at that point, left hand side we've got gas pressure. What about the right hand side? On this right hand side, we've got the fluid pressure acting above. This fluid pressure is acting on this area, on this place, and this fluid pressure has a height H. Okay, then this is also open to atmosphere. So we have got atmospheric pressure also acting because it is open tube. Okay. So on the left hand side we have two pressure. One is the atmospheric pressure acting, and the other is the fluid pressure which is acting. So on the left hand side, if I see at this point, point number 2, or sorry, point number right hand side, we have got the fluid pressure plus atmospheric pressure. Sorry. So we write this as P gas is equals to atmospheric pressure plus fluid pressure, which is rho G H, fluid. So this is how we divide. First, we find a point where the pressure is equal. So in manometer calculation, we find a point where pressure is equal. Okay. So left hand side pressure is equal to right hand side pressure based on the Pascal law. Okay. Then we put the values of left hand side and right hand side. So on the left hand side, we've got only gas pressure acting, and on the right hand side, we have got the atmospheric pressure plus the fluid pressure acting. Is it clear or should I repeat? How we get this gas pressure? P2. P2 is the gas pressure. Here. So P2 is also P1. P1, which is the gas pressure, is equals to P2. So P1 is equals to P2. This is equals to atmospheric pressure, which is acting, plus this height. Okay. We will solve the numerical, then it is easy to understand. Okay. Don't worry. So this is simple type of manometer. Okay. Next, we move on to the same idea which I've already told you guys. Okay. We have got a tank. In that tank, you've got some pressure. Okay. Okay. That pressure is acting here. Okay. Now this is the manometer fluid. This pressure caused this fluid to push down, and from here it move up. Now rule number 1, find a point where the pressure is equal on the left hand side and the right hand side. Rule number 1, find a point. Rule number 1, find a horizontal line where the pressure at the left hand side is equal to the pressure at the right hand side. So in this figure, where is the location where the pressure at the left hand side is equal to the pressure at the right hand side? This part. So this part, the pressure is equal. This line. Okay, this pressure and this pressure is equal. Same height. Okay. So what is the pressure on this line? On this line from the top, the pressure is PA. And on this line, the pressure is atmospheric pressure. This pressure, atmospheric pressure acting here on top of the surface, plus the fluid pressure. Okay. So Z. So this is fluid pressure. So now let's go again. Let's do again this thing. If cannot understand, please ask me. Otherwise, it will be difficult later on. Okay. Ask me again if cannot understand. This is the last slide. After this slide, I will finish. Okay. This is the last slide. So this is my pipe. In this pipe, I've got two locations. This location so we've got location number 1. This is, let's say, location number 1, and this is location number 2. Now I want to find the pressure difference between location 1 and location 2. Okay. So we've got fluid inside. The same fluid is filled until here. Then we have got a different fluid. Here got a different fluid until here. And we've got the same fluid here also. This fluid has a density rho 1. This fluid has a density rho 2. The height from here to here is A. The height from here to here is H. Okay. Now manometer function is to measure pressure difference. So calculate pressure difference P1 minus P2. How to calculate? Remember rule number 1. Find a horizontal line where the pressure is equal. Okay. So this is the horizontal line, this one. Okay. At this point the pressure is equal. So left pressure at the left hand side is equals to the pressure at the right hand side. Okay. What does it means? Let's calculate left hand side. Left hand side is like this. On the left hand side I've got only this pressure. And on the right hand side I've got two types of pressure because got two types of fluid. This fluid from here to here is A. This fluid from here to here has a height of H. Okay. At this point and at this point the pressure is equal because they are on the same horizontal surface. Okay. Understand? Getting until now can understand this? Any confusion?
No, sir.
Okay. Okay. So pressure at the left hand side is equals to the pressure at the right hand side. Okay. I will finish the class. Pressure at the left hand side is equal to pressure at the right hand side. Okay. So what is the pressure at the left hand side? Okay. This height is how much? A plus H. The vertical height pressure varies with respect to vertical height, not the diagonal height. Not the diagonal height, the vertical height. So the vertical height is A plus H for this fluid. This is the same fluid which is density rho 1. Here also is density rho 1. Here got density rho 2. Okay, you can see in the figure. So what is the pressure? Pressure is equals to rho GH. So on the left hand side, pressure is equals to density 1 multiplied by gravity, which is same, multiplied by height. What is the height? The total height of this fluid, rho 1, is equals to A plus H. So I write here A plus H. This is equals to the pressure at the right hand side. What is the pressure at the right hand side? The density of the fluid only for this fluid 1. This fluid 1 is until A only, height. This fluid 1 is present until height A. So I write rho 1 into G into A plus we have got this height also, fluid 2. So fluid 2 is rho 2. Fluid 2 has a density rho 2 for a height of H plus rho 2 into G into H. Okay. So rho 1 G A plus rho 1 GH is equals to rho 1 GA plus rho 2 GH. Okay. Plus on this upper side we have 0.1, so pressure 1, and on this upper side we have got 0.2 or pressure 2. So we write here also P1 plus P2 plus on the left hand side. Here also P1 plus, we got P2 plus. So pressure difference P1 minus P2. What is pressure difference P1 minus P2? First we cancel the common term. So rho 1 GA cancel. So P1 minus P2 is equals to rho 1 GH, sorry, rho 2 GH minus rho 1 GH. Okay, so P1 minus P2 is equals to GH common rho 2 minus rho 1. So if I want to find a pressure difference in with the help of a manometer, this is how I can calculate pressure difference.